Our next talk is going to be Rooted Clusters for Graph LP Algebras by Elizabeth Kelley.
Awesome, thank you. And thank you to the organizers for putting this together. I've really enjoyed it so far. Maybe I'll just get started then, since we're a little behind. So I'm going to talk, like my title indicates, about rooted clusters for graph LP algebras. And the sort of basic outline of the talk is that I'm going to give some brief background and definitions. I'm going to show you some formulas that we have, and then a combinatorial construction that gives us interpretations for certain coefficients in these formulas. And I think the thing that I want to say before I get started is because this is a 20-minute talk, what I primarily want to do is I want to give you sort of the narrative arc of the project. So there are places where I'm going to gloss over precise definitions or technical details, just because if you're familiar at all with cluster algebras or LP algebras, you know that some of these definitions take a lot of time and notation to state precisely. And I don't think they'll give us a lot of insight in a talk this short. Okay, so first of all, for those who have not seen cluster algebras before, these were introduced in 2001 by Fomin and Zelvinsky, and they're commutative rings with a certain set of generators, x1 through xn, called cluster variables. And these generators appear in overlapping subsets of fixed size called clusters. And each cluster is sufficient to generate the entire algebra. So this is one of the sort of hallmark structural characteristics of a cluster algebra, that I don't need to tell you the entire set of generators. I can tell you a specific size subset of the generators, and you can tell me the rest of the algebra. And so there's a relation between different pairs of clusters. So if I've got one cluster C and I want to somehow move to a new cluster C prime, I do that by a process called mutation, where I take a cluster algebra in one cluster, or sorry, a cluster variable in one cluster, and there's a unique way to exchange it for a distinct cluster variable in a cluster that it's related to by a single mutation. And so if I have a sorry, I'm just getting the pen up. So if I have a cluster that looks like x1 through xn, I can do this at any cluster variable. So there are n ways to mutate this cluster. And to reach an arbitrary other cluster, I may not be able to do that in a single mutation. I may have to do a sequence of these mutations. Okay, and so then let me say a little bit about what the relation between the cluster variable that I'm starting with and the cluster variable that I'm swapping it for. So in a traditional ordinary cluster algebra, these relations look like binomials. So on the left-hand side, you'll always have a product of the variable that you're swapping and the variable that you're swapping it for. And then on the right-hand side, you'll have some binomial that's determined by some additional data that I'm not telling you about. But this is an example of what these relations might look like. And two sort of hallmark properties of cluster algebras are, the first is called the Laurent phenomenon. And so this says that even when I start composing mutations, so once I start composing mutations, my right-hand side might not look like a binomial, right? It's going to be some composition of these binomial relations, and it may end up with more terms. But the Laurent phenomenon is this sort of miraculous property that no matter how I compose mutations, they're always going to cancel and give me something that looks like a Laurent polynomial. And even better, I have what's called positivity, which says when I do this cancellation, even though it's not a priori obvious that canceling polynomials is going to give me something with positive integer coefficients, I actually end up with the Laurent polynomial with positive integer coefficients, which should immediately jump out at you as maybe something that's hiding some interesting combinatorics, right? Because as a combinatorialist, I see positive integers and I want to start counting things. Okay, but so we're actually not going to talk about ordinary cluster algebras. So in 2016, Lam and Pylyavskyy introduced a generalization of cluster algebras called LP algebras. And the idea here is that now we're letting the exchange relations be more complicated. So this sort of question that I see this as trying to answer is, how much can I relax the conditions for a cluster algebra and still get something with the Laurent phenomenon? So now we still on the left-hand side have this product of our old variable and our new variable, but now on the right-hand side, we let these exchange binomials instead be Laurent polynomials. And there are some conditions on what these look like, and I'm not going to say anything about that. What's important for you to know is just that there's some Laurent polynomials. Okay, and so a theorem that they proved in this paper was that these algebras actually exhibit the Laurent phenomenon, right? They do what they were cooked up to do. But left open as a conjecture was that they should also exhibit positivity. And it turns out this is actually quite hard to think about because LP algebras are quite general, as you might imagine from how general these exchange relations have gotten. So we're actually going to focus on a subset of LP algebras called graph LP algebras. And these are LP algebras that have a certain visualization in terms of graphs. So the idea is that I take some simple graph on vertices labeled by 1 through n, and I'm going to cook up some cluster variables based on collections of subsets on these graphs. And so specifically, I'm going to care about what are called nested collections of subsets.
Excuse me, are the I sub j's vertices?
No, they're going to be subsets of vertices.
Oh, okay, thanks.
Yeah, thanks. Yeah, please ask if any of my notation is not clear. I have tried to condense this, but I may have missed a key piece of notation. Right, so each of these I sub j are supposed to be a subset, and then S is a collection of subsets of vertices. And I say that these are going to be nested if for any pair of subsets, either one is a subset of the other, or they have an empty intersection. And then the other condition is going to be that if I look at some tuple of disjoint subsets and I take the strongly connected components of their union, I get back that tuple of subsets. So this definition might be a little opaque. So I drew some examples of collections of subsets that are considered nested. So for example, if I look at this leftmost drawing, I can see that if I take any pair of subsets there, either they're going to have an empty intersection if they're distinct subsets, or one is going to be equal to the other, right? Maybe a little bit more interesting. If I look at one of these other subsets, I can again see that I'm meeting this first condition, and even better, I'm meeting, in fact, the second condition as well. And then I drew also some non-examples. So here in the leftmost drawing, this is meeting condition 1, right? If I took a pair of subsets, they all have empty intersections, but it's not going to meet condition 2, because if I take, say, vertices 1 and 2, and I take their union, then the strongly connected component of the union is the subset 1, 2, which is not either of the subsets I started with. Okay, and so then the LP algebra that I'm defining from this graph, well, it's going to have some grounding, which is z adjoins some variables a1 through an. And then it's going to have 2 types of cluster variables. So I'm going to have one cluster variable for each AI, so x1 through xn. And then I'm going to have y cluster variables. And these are indexed by subsets of vertices. So I have one for each vertex subset where I get a strongly connected component of the graph.
What does strongly connected mean?
So I think you can just think about it as connected.
Okay, thanks.
Okay, and so then my clusters here are going to look like collections of possibly both x and y variables or just one, where the condition is that if I look at the subscripts of all the y variables, that has to give me a maximally nested collection of subsets. And then the vertices that appear in those subsets can't appear as subscripts of x variables. So it might not be immediately clear just from looking at the definition, but this will give us also a unique way that we can swap out variables when we mutate in each direction. So just to give you some examples on this graph that we've seen already, some clusters here are, well, I could take an x variable for each vertex, or let's say that I took the x variables for vertices 3 and 4, then I just look for a maximally nested collection of subsets on vertices 1 and 2. And one way to do that is to pick vertex 1 and the subset 1, 2. Or I could have a cluster that's all y variables, where here what I've done is I've chosen vertices. This should be a 2, not a 1. Yeah, so sorry, this should be a 2. So then I get 2, 3, 4, and everything. Okay, and then the next natural question is, okay, what do the exchange relations look like here? Actually defining these takes probably a nice 7 to 10 minute detour if you're going to define all the notation very well. So instead, what I'm going to do is I'm going to tell you what types of variables I can exchange. And I'm not going to write down what the actual exchange relations look like. So I can exchange x and y variables if they have the form xi and y so plus I, where so plus I indicates, so I take the subset S, I take the vertex I look at their union, and then I choose the connected component that contains the vertex I. And then I can also exchange y sub so plus I and y sub so plus j. So to give you an example, let's say that I start with this cluster. So I have x2, y1, y4, y5, y1, 3, 4, 5, and then y sub everything. One exchange that I could do is I could swap out y sub 1, 3, 4, 5 for y sub 4, 5, 6. So what I've done here is I've taken the union. So here S is the set of vertices 4, 5. And then I've taken the union with, okay, so, and then maybe it should be, yeah, so here I is 3, I think, so this should be 1, 4, 5. J is 6. When I take SO plus J, I should get this and this, right? And then if I look at the connected component that contains 6, I just get this component up here. So I'm left with y sub 4, 5, 6. Okay, but it turns out that.
Excuse me.
Yes.
Sorry to ask. Your all example were bipartite graph. Is there any connection because we see something like that in algebra? I mean, the original motivation for defining this LP algebra.
Oh, I see.
Examples are all bipartite graphs.
No, it's a coincidence that I've been drawing bipartite graphs.
Sorry, thank you.
No, it's a good question, but yeah, it's a coincidence. The graph LP algebras are defined for any simple graph. Okay, but so it turns out that thinking about positivity in graph LP algebras is still hard. So we're going to further narrow our focus to what we call rooted clusters. And the idea here is that we're going to only think about tree graphs And for a tree, you can pick a vertex and consider that as the root, right? And so then once you choose a root, you can think of your tree as a poset where the root is the maximal element and cover relations are given by the edges of the graph. So just to give you a little bit of useful notation, you don't need to remember this notation, but it will show up in some formulas. So I want you to have at least seen it. So if I'm thinking about any vertex other than the root, I'll use I plus to denote the element that covers it. And then I can use a combination here of, so here gamma would stand for the graph. V, the superscript, tells you the root on the graph. And then the subscript is telling you what vertices to look at. So here, these would be the set of elements covered by I. And then similarly, I could do the set of elements covering I, all elements strictly less than I, less than or equal to I, and so on. Okay, and so there's exactly one rooted cluster for each vertex of our tree graph. And so another piece of notation that we use in these formulas is for each vertex in our graph, we're going to let I sub x be the collection of elements that are less than or equal to x when we view this as a poset. And so then we'll say that the rooted cluster that for vertex D is the collection of I sub x for where x ranges over every vertex in our graph. So for example, here, if I think about 1 as the root of this tree, then this is the rooted cluster. So you can think about it as at each vertex, I just take the collection of every vertex that is that vertex or below it in the poset. And so one thing that you can quickly check is that these rooted clusters are in fact legitimate clusters in your graph LP algebra because they give you maximal nested collections of subsets. Okay, and then my disclaimer for these formula slides are I'm going to show you a lot of sort of nasty looking formulas. We're not going to linger too long on them. What I want to show you is I want to show you, one, that they exist, and two, to point out some quick structural features. So, okay, the first formula is basically saying that if I look at the y variables for certain subsets of vertices, I get things that look like products of y variables in my rooted clusters. And so the thing that I want you to notice here is that these are going to have positive integer coefficients because they're just products of variables in my cluster. And they're going to be useful notation because now whenever I see one of these in a formula, I know that it's hiding, it's not hiding anything that would get in the way of positivity. Okay, so the next formula is that for the x variables, I can write them in this form. And this is quite messy looking, but the thing I want you to notice is that all of the variables that you're seeing show up here are either variables that we just saw, we can write as products of things in our cluster, they're variables in our cluster, or they're some variables that are just part of our ground ring. And that the denominator is just a product of variables in our cluster. And so that means that as a corollary of this formula, we can see that these, when we actually expand these expressions, that we're going to get Laurent polynomials with positive integer coefficients in terms of variables in our original cluster, which is what we were after. And so then the sort of next formula is, well, we have another type of cluster variable, right? We have these y variables. So again, we can write a formula here where if we look at each of the variables that show up on the right-hand side, they're either variables in our cluster or variables that we saw we can write as products of elements of our cluster. So again, as sort of an immediate corollary of this formula, we get that these variables can be written as Laurent polynomials with positive integer coefficients. Okay, and then I'm also conscious of time. I think I have maybe 3 or 4 minutes left.
You have till 11.
Oh, okay, great.
I believe so.
Great, okay. So what I want to try to quickly tell you about, though, is as a combinatorialist, when I see these positive
Oh,
integers.
yeah, actually, no, sorry about that. About 3 minutes. It's fine.
Okay. So I'm going to tell you an abbreviated version of this story. So as a combinatorialist, when I see positive integers, I want to count things. And if you are familiar with cluster algebras, you know that there are these constructions called Tpads that are one way to prove positivity in certain types of ordinary cluster algebras. And so I'm not going to step through all the details, but the idea is that in certain types of cluster algebras, we can relate there's a model of the cluster algebra in terms of a triangulated surface. In particular, for type AN, there's a model in terms of triangulated polygons. And so you can define something on these polygons called a Tpath. And I'm not going to go through the rules, but basically, depending on the variable that you're trying to find a formula for, your original triangulation is going to encode the variables in your original cluster. You're going to draw a new arc, like this orange arc, and then something about the geometry of the way that it crosses the arcs in the existing polygon is going to tell you how to write down an expansion for your new cluster variable. And because the coefficients in this expansion are now going to count certain types of what we call Tpads, they're sort of manifestly positive integers because I can't have a negative number of some object. And so it's known from the original paper that the path graph can be identified with a cluster algebra of this type. And so this is sort of our inspiration for our combinatorial construction. So we take a path graph, we extend it by adding a vertex on each side. Our Y cluster variables now show up as arcs here. And if you think about folding this together and adding an edge between the primed vertices, you get a triangulation of a polygon where you can play this game with Tpads. Okay, and so then it gets a little more difficult. You have to do something new if you just have a tree and not a path. So the sort of essence of the idea here is that you extend each leaf to a primed vertex, and now you add edges that are potentially hyperedges representing each vertex subset. So these hyperedges join the neighbors of your vertex subset. And then there's a way to come up with what we call hyper Tpads, where now some of the edges might be hyper edges, so they connect more than two vertices. And so I'm absolutely not going to go through this, but you can write down a set of rules for these hyper Tpads and prove that they produce these consistent objects. And then you get an expansion formula from these hyper Tpads that gives you a way to get the expressions for other cluster variables in terms of your original cluster using this combinatorial construction. And I guess the last thing I want to say about it is, just like in the ordinary cluster algebra case, this gives you a combinatorial proof of positivity, because now the coefficients in your expansion formula are counting hyper Tpads with certain properties. And if you wanted to read more about any of these things, there are some references, but otherwise, I guess I am out of time and at the end of my slides. So I'll just thank you for listening. And this is one of my, this is an exchange graph for all of the all Y clusters of a certain graph that I drew once and had to use because it took a while to draw. So thank you for listening.